Welcome back to another explainer. So today, we're diving into what feels like a bit of a scientific paradox right at the intersection of high-level physics and everyday lab work. We're talking about dynamic light scattering, or DLS. Now, if you've ever worked in a lab, or if you're just fascinated by how we measure the microscopic building blocks of our world, you know that precision is absolutely everything. But what happens when one of your most precise instruments tells you it actually doesn't need to be calibrated?
Section 1. The calibration confusion. Picture this. You've just unboxed this gorgeous, highly sensitive DLS instrument. Your absolute first instinct, because it's been drilled into us since day one of science class, is to calibrate the thing, right? You look for the baseline settings, you check for the reference materials, and there's nothing. Zero. Which brings us to the exact question clients frequently ask the experts over at Brookhaven Instruments when they're trying to validate their tools. Why on earth is there no calibration for dynamic light scattering? Honestly, it feels incredibly counterintuitive. In almost every other analytical technique, calibration is the literal bedrock of accuracy. You weigh a known standard, you zero the scale. But DLS completely flips this script. There's a quote directly from Brookhaven Instruments that captures that sheer disbelief perfectly. They say, "At times we are met with confusion when we state there is no calibration and that DLS is not a calibrated technique." And it's totally understandable why folks are shocked to discover their advanced instruments are officially uncalibrated. It kind of feels like flying blind. But as we're going to see, it's actually the exact opposite.
Moving on to Section 2, the power of first principles.
So, the secret to this missing baseline boils down to a concept called first principles. What does that actually mean? Well, a first principles technique is an absolute technique. It calculates results straight from the fundamental underlying physical laws of the universe, rather than relying on some empirical calibration against a standard. Think of it like this. Instead of measuring a footprint by comparing it to a known shoe size, you're literally calculating the size of the foot by understanding the very physics of how that foot interacts with the ground. You're going straight to the source. To really put that into perspective, let's contrast DLS with something we all know well, chromatography. Chromatography is a relative measurement. You absolutely have to run known standard reference materials through it to create a map, and then you compare your unknown sample to that specific map. DLS, on the other hand, it's an absolute technique. It relies purely on physical laws and math. There is no map required because the territory is already defined by the absolute laws of physics.
And the real crux of it is this. The relationship between a particle's size and how fast it diffuses, or moves through a liquid, is mathematically defined, period. This is a profound concept. Because this physical relationship is an ironclad mathematical guarantee, you can completely bypass those empirical reference curves. The math literally does not lie.
Which leads us to Section 3, Brownian motion and light.
Okay, so how does this actually play out inside the instrument? Let's break it down. Step 1. The particles in your liquid are undergoing Brownian motion. They're just randomly jittering around as they collide with solvent molecules. Step 2. You shine a laser on them, and this random movement causes these tiny fluctuations in the intensity of the scattered light. Step 3. The instrument captures all that fluctuating data and analyzes it. And finally, Step 4, boom, the particle size is derived from that analysis. But wait, what exactly connects Step 3 to Step 4?
Well, the answer is a truly beautiful piece of math known as the Stokes-Einstein equation. This theoretical model is the critical bridge. It translates those physical light fluctuations directly into a super precise particle size. Basically, it takes the speed of that Brownian motion, which we literally just measured from the light, and mathematically works backwards to tell us exactly how big the particle must be to move at that specific speed. No calibration standard needed, just pure, elegant physics doing its thing.
Now for Section 4, why traditional calibration fails. Let's play devil's advocate for a second, though. Say you just wanted that warm, fuzzy feeling of peace of mind, and you tried to force a traditional calibration onto a DLS system anyway. Turns out, it would totally fail. See, DLS relies inherently on theoretical models and assumptions. Because it's an absolute technique, the accuracy of DLS depends entirely on whether those specific theoretical models are valid for your sample rather than checking it against some physical baseline standard.
Think about it like this. If the assumptions in the model don't perfectly match your real-world sample, a traditional calibration is absolutely not going to save you. There are simply way too many complex variables at play here.
I mean, for the model to work flawlessly, it has to assume spherical particles, dilute suspensions, and known refractive indices. And that's before we even talk about the instrument factors. You've got physical alignment, the exact laser wavelength, detector sensitivity, the scattering angle, and the optical properties of the sample itself. You literally cannot use a simple standard calibration curve to magically calibrate away a slightly different scattering angle or some weirdly shaped particle. It's just too complex.
So because of all that, we really need to frame DLS accurately. It is technically considered a non-calibrated or semi-quantitative analytical method, right? It is not a rigidly calibrated scale like you'd find weighing out turkey at a deli. Instead, it's this incredibly powerful analytical tool that gives us rapid, deeply useful information about particle size distributions, all based strictly on the physics of the sample itself. Which brings us to Section 5, a legacy of scientific breakthroughs. So why does this all matter to us? Well, understanding this uncalibrated technique is literally unlocking the future in massive fields like nanotechnology, pharmaceuticals, and material science. Companies like Brookhaven Instruments use this pioneering light scattering tech to fuel modern scientific breakthroughs across the board. I mean, think about it. When you're developing some cutting-edge, life-saving drug delivery system at the nanoscale, or engineering a totally revolutionary new material, you need the rapid, first principles analysis that really only DLS can provide. You absolutely do not have the time to sit around inventing calibration standards for materials that haven't even existed until today.
Which leaves us with a pretty fascinating thought to chew on. As we push further and further into the microscopic world, creating entirely new things we've never even seen before, standard reference materials simply aren't going to exist yet. So how will first principle analytics like DLS continue to shape the future of these uncalibrated discoveries? Well, it turns out that by letting go of the training wheels and trusting the fundamental laws of physics, we're actually freeing ourselves to discover the unknown. Thanks so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.